All right, so the main goal of a binary tree is to organize it in such a way that data can be searched. Now, right off the bat, we know that a binary tree has the data stored in an organized order, right? So that's the nature of a binary tree. As we add things in, it plink goes down into position. So now we need to think about different ways that we can actually search for information inside of a tree. We're looking at this at a pretty high level where we just have numbers and we're just haphazardly deciding, I want to find the number 5 for no good reason. Where if we try to apply these search techniques to something maybe a little bit bigger, where, let's say we have, instead of holding numbers or instead of holding strings, maybe we're holding objects, patient records or something like that, and maybe they're ordered by last name, something along those lines. But now when we search we're searching through the tree, maybe they're ordered by last name, but maybe we're searching for a patient record that has a certain date of birth, or that has a certain ailment, or something like that. So the type of data we can hold in our tree can be much more complex than just numbers like we're looking at right now. So we want to have a way of getting at those records fairly quickly, and these are the generically speaking, trees are our support structure for databases. When we think about database management systems, how many of you have had or in Professor Wall's database class? Okay, so the way those guys, you're probably dealing with what, MySQL? So MySQL is a relational database system. It's written in terms of trees, in terms of an evolution of binary trees. All right, so these need to be fast when we're searching this stuff, or at least reasonably fast. So we have different strategies for how we can look through a tree. So breadth first search, trees can also be traversed in level order, where we visit every node on a level before going to a lower level. This search is referred to as a breadth first search, as the search tree is broadened as much as possible on each depth before going to the next depth. Now, we know, if we look at the nature of our tree, let's just go back up to this guy here. When we look at how a tree is organized, these are the leaf nodes, A, C, E, H. So if we think about the pattern of our tree, these guys would be, what could you say about these guys in our tree? A, C, E, H, as opposed to B, D, I, as opposed to F, G, something like that. What could you say about these different layers? F, B, G, A, D, I, C, E, H. What kind of conclusions might you make about those in a binary tree? Which element was added first in this tree, E or B? B was added first. It's been in the tree a longer period of time. Now, at this point, we haven't talked about anything with tree rebalancing and the depth of a tree. So it would probably be relatively fair to say that the higher up in the tree we are, the older the data in our current view of binary trees. Could we imagine situations where searching for older data first might be more efficient? Let's say we're looking at through news articles or something like that. We're looking through news articles, and really the first thing that comes to mind is that we might want to reverse that. You might want to search the newest data first, and then so you might actually want to do a level order in reverse. Go to the bottom of the tree and work your way back up, because that's probably going to hit the articles that are most recent without any sort of rebalancing algorithms, which we'll talk about next when we talk about AVL trees. All right, but certainly we can come up with examples where the age of the data, or the likely age of the data, might have some meaning to us in terms of searching it. Make sense? So that's when we might use a level order, or I usually just coupled it into a breadth first search. For some reason, since it's the only way they talk about it, I usually just call this a breadth first search, and I don't really differentiate the depth first searches in terms of being anything special. This is just the various ways we can visit nodes. All right, so having said that, if we want to visit this tree, in breadth first order. So that is F, B, G, A, D, I, C, E, H. How would we pull that off? We're going to think about an algorithm. It's already organized like this. So the easy first step is we could visit the root node, right? That part's easy. At tree, roots not equal to null, visit. We're there. Okay, well, now what's next? We need to visit this guy's left node, and then we're going to visit this guy's right node. Then we're going to visit this guy's left node and his right node, and then this guy's left node, if there was one, and his right node. Then we're going to visit this guy's left node if there was one, and his right one if there was one, and then this guy's left node and right node, and then this guy's left node and right node if there was one. Similar at this final level. So how do we implement that? We wrote our depth first searches kind of recursively, right? Fakesy recursively. So you're not actually calling the same method, you're calling it your left child's visit in order type method. So how would we actually implement the solution to this problem? So we just understood what the problem is, right? So we know what we're trying to do. We just talked about the high level, how we need to actually visit these. So now we need to come up with a recipe for actually going through these in the right order. All right, so let's start kind of at the top. Very first thing is we're going to visit. So let's get our algorithm for level order, which that's going to be a very uncomfortable term for me because I've literally never called it level order. But we'll follow the things. I always just call it a breadth first search. All right, so algorithm for level order. We're going to say if we have a root node, visit it. That's happening right off the bat, right? So if root not equal to null, visit it. Okay. Step one, easy. Now we need to look at step two. All right, so now once I've done that, what do I need to visit next? Well, next we're going to visit the root node's left child. All right, and then we're going to visit the root node's right child. But we're going to visit them in that order. We're not going to let it daisy chain down recursively. These aren't recursive calls. This is saying visit left, visit right. Period. Don't do any more than that. So we're going to say visit roots left child, visit roots right child. All right, so first three steps now. Then what? Whose left and right child do we visit next? Root's left child, we visit his left and right child. Correct? So now we're going to say visit root's left child's left child. Visit root's left child's right child. Then visit root's right child's left child. And right child's right child. Keep going down as it's going to get wider and wider, right? Okay, so now we need to start finding a pattern, finding an algorithm in this. So we could, when we look at this picture here, initially, if we just think about the top of our tree, this is a list of one node to visit. Then the next level, we have two nodes to visit. This is a list of two nodes. Then the next level is a list of three nodes in this example, right? It could be as much as four nodes. So 1, 2, 4, 8, so on and so forth. So really what we can do is we can create linked lists of the nodes that we want to visit and then visit those linked lists in order. That makes sense? And build up the next list. All right, so let's think about how we can rewrite this algorithm. So if root is not equal to null, add it to a list of elements to visit. All right, so let's just dump this stuff. All right. Then, and what we could actually do is we can build that list first and then actually do the visiting. That make sense? So let's think about building that list. So we added the root node to our list of elements to visit. So if we use our example, this guy's what? So we'll add F to our list. We'll just build it off this. So we just, so here's our linked list. So there's our F so far. All right. Then we need to add roots left and right to the list. Add roots left and right to the list. So in this example, that's B and G. Okay, those guys are added to the list. All right, so now what do we do next? We know at this level we have a maximum of 2 things, but potentially there was just 1, or potentially there was even 0. All right, so we can't necessarily rely on this is level 1, this is level 2. We can't necessarily rely on that. All right, but so far so good. Now what? That was a good one.
You can hear that from all the way
Oh yeah,
oh,
especially the second one. I'm envious. The cruise ship bed has done a number. Probably not as bad as the Guatemalan prison. I was probably sleeping on chicken bones. All right, so we have our, we've added the roots left and right, but now we need to work down the tree. So we go back to this picture. So now we're kind of dangling somewhere in here. We need to find a way to start taking a wire, taking a rope and moving down the tree, right? All right, so we need to get to this level. So we've added this guy to the list, then we added this guy and this guy to the list. We were able to do all that from this level. Now I need to drop down to this level and see the world through this guy's lens and see the world through this guy's lens. Now we know we want to add this guy's children to our list next. And then we want to add this guy's children to the list next. But we don't want to add this guy's children until we've already added this guy. Right? We need to make sure G is in line before we add B's children. All right, so how do we get down our list from that perspective? This becomes difficult because of the way we're traversing the tree. Depth first searches, all those different in-order, post-order, pre-order stuff, was easy because we can rely on that fake C recursion. Okay? Fake C recursion is only going to get us in trouble here. All right? It's going to take us too far down the list and we're going to lose our spot. So any suggestions? Based on what you know? Only on the data structures you're currently familiar with? What about a stack? Could we possibly use a stack here to pull this off? Think about the nature of a stack data structure. Push, pop, peek. So let's start building this up as a stack. So rather than us adding it as a list, let's start adding stuff onto a stack. All right. So if this is our stack, it would have looked like this. We would have pushed F onto the stack first. Then we would have pushed B onto the stack. Then we would have pushed G onto the stack, like that. All right, F, B, G. Now we know the next person whose children we need to get is B's children. How do we get at B's children from this stack? We know that our top two guys here are the current level we're looking at, right? We just pushed them because we're still sitting up here we're still sitting at root. Sitting at root currently. That's the level in our tree where we're currently viewing the world through. That's the porch we're looking at. All right. So we know that this guy is root, and everything besides him, everything besides the very last element in our stack right now, must be my children. All right. Now, could we have two stacks? Is that allowed? Could we have two stacks working in conjunction with each other? Might I have a secondary stack here where I can pop off G, push it on here, pop off B, push it on here. So now this guy's back looking like that. So now those guys are in the correct order. So what happens next? I know I need to get B and G's children, but where do I put those guys? Do I maybe have a temporary stack? Who are B and G's children? A and D? Push, push. And then what do I do with B? Push. Then I get G's children, which is just I. Then push. Now we're empty stack. Pop push here. I, D, A. That empties that stack. Now we're going to get A's children. Nothing, nothing. So get A's children, push them on here. That's nothing. Pop A. Push A. Get D's children. C, E. Push, push. C, E. Then pop, push D. Then get I's children, just H, push, pop push, pop push all those guys, H, E, C, get C's children, nothing, E's children, nothing, H's children, nothing, push, or pop push. Once this list is empty, we know that we are done. All right, so this is what our stack currently looks like. By the way, remember earlier I said you might be interested in the newest news articles first? HEC, IDA, HEC, IDA, GBF. So that current stack up there literally would have me visiting the tree upside down breadth first. Make sense? If I want it in the right order, what do? I just pop push. So H, E, C, I, D, A, G, B, F. F, B, G, A, D, I, C, E, H. F, B, G, A, D, I, C, E, H. Make sense? All right. So now we need to actually put that into some English terms that we can follow. So we visually have solved the problem now, right? Using really 3 stacks. Okay, so we needed 3 stacks. We had our initial visit stack, and then we popped off that stack, right? So let's kind of go back here. And now that we've kind of seen how this works, let's do it one step at a time and record the actions. All right, so very first time, what we start off is empty. If root is not equal to null, and let's give these guys names. Let's call this guy content stack. Let's call this guy child stack. And let's call this guy temp stack. So we have some names we can refer to them from. So if root is not equal to null, push onto content stack. Okay, that gets us the F. All right, so now we have the content stack there. All right, so now what are we going to do from there? Gotta decide whether content stack was the correct place to put F, or was content stack where F is going to ultimately end up. Remember our cadence we just went through. We usually had stuff in here, and then we loaded its children into temp stack. And this guy did not leave here until temp stack was full from his children, and then put onto content stack. So really, this should be child stack. So we'll start with F, in this case, the root node, on child stack. Then, while child stack has stuff, add, push the left and right children of peak child stack onto temp stack. So that's BG, pushed. So push B, push G on top. Okay, push, push. All right, push the left and the right child. Actually, let's put these in 2 lines, so that's cool. So we'll push the left and right children of peak child stack onto temp stack, then pop from child stack and push onto content stack. So we peeked at this guy to find out who we're dealing with, get that node. Then we pushed his 2 children onto temp stack. Then we pop this guy off of child stack and push onto content stack. And that's while child stack has stuff. Okay, child stack no longer has stuff. So now we're back here. So child stack has nothing in it. What do I do now? Doesn't temp stack become the new child stack? But in push pop order, or pop push order, sorry. So now we need to say while temp stack has stuff in it, pop push onto child stack. So what we're effectively doing here is we are going to move contents of temp stack onto child stack in reverse. And let me actually make that caps and bold. Okay, and the reason I do that is I want to emphasize something here. We've already seen it happen, but one of the major uses for a stack data structure is to reverse data. Okay, and we're seeing that happen over and over again here, right? Okay, it's a very convenient tool for doing that. All right, so in reverse, and that is the pop push move, right? You have two stacks, you can pop push, and that reverses the guy that was the original. So we will, so what does this ultimately say? It says while, let's get out of bold here. While temp stack has stuff, pop push onto child stack. So that'll be G, B. But we popped, so they were removed from there. Make sense? All right. So as long as child stack has stuff, our job is to fill temp stack. Then our job is to empty temp stack back into child stack. Now child stack has stuff again. So all this stuff, both of these moves need to keep happening as long as both child stack and content stack, or I'm sorry, child stack and temp stack have something. As long as at least one of those guys has at least one guy, we need to keep going through this whole cadence. Okay. So let's kick this down. So while there is at least one element in child stack or temp stack, do the following. So we're effectively clearing child stack, right? And that's really what this says. Clear child stack, and that's going to require us to do this. That should be good enough. All right. So while there's at least one element in one of those two stacks, we need to clear child stack. Then we need to move child stack back into temp stack. Or I'm sorry, temp stack back into child stack in reverse. And we're going to keep doing this over and over and over again as long as child stack or temp stack have something in them. Okay? When we're done with that, when we finally exit this guy, we know child and temp stacks are empty and all of our nodes are in content stack, let's just say in reverse order by our level first approach. They might be in the right order if we're searching for newest to oldest news things, something like that. All right. Okay, but they're in reverse order. So we need to reverse them again. Okay. So just kind of let's follow our steps here and make sure we captured everything. So while there's at least something, let's go back here, keep the F in there. So we initially loaded into child stack our F. Then while there's at least one element in child stack or temp stack, do the following. So there is one element in child stack, there's 0 elements in temp stack, we're good to go. So what are we going to do? While child stack does stuff, we're going to process child stack first. While it has stuff. So we're going to push the left and right child of peak of child stack onto temp stack. So we'll just peek at the top of child stack and get the F. That's that node. We'll go ahead and grab his left child if there is one. We'll grab his right child if there is one. And we're going to push those guys onto temp stack. So that is left child is B, right child is G from the peak of child stack. So there's the B pushed, there's the G pushed. Then pop from child stack and push onto content stack. So we pop, then we push. All right, so that finished this right here. We spin back up. Is there still stuff inside of child stack to process? Right now, there is not. So we fall out of this while loop, and now we move to this next thing where we're going to move the contents of temp stack into child stack in reverse. So while temp stack has stuff, which it does, out of curiosity, how can we ask if a stack has stuff in it? How do we ask that question? How might we ask, while temp stack, does temp stack have at least one element in it? How do we ask that question?
Equals null, right?
If what equals null?
If the stack, what's in the stack?
Okay, well, that's a pretty broad answer. Tell me more detail. I have this stack sitting here. It's an actual thing. All right, we'll use your card as the example. This is a stack. All right, it's an actual thing. And here we'll put one thing on top. That's actually, we're gonna go that route because the phone's a little bit bigger than the card. There we go. All right, I wanted to be able to read the joke. All right. So there's our stack. How do we ask, does this stack have at least one element on it? Or ask, is this stack not empty? Peek. I'm going to peek at the top of the stack, and if I see something there, there's at least one thing on the stack, right? If I get a null out of that, when I call peek, if I get a null, that means there's nothing on that stack. So I'll peek at the top of the stack. I'll get the value. I haven't removed it. I sort of kind of removed it. We'll just leave it there. Okay, we're just peeking at it. I see, oh, there's something there on the stack. That means that stack is not empty. So while temp stack has stuff, which in this case temp stack has two stuffs, right, G and B, but I'm going to peek at the top of it and say, oh, I found something that's not null. That means it has stuffs. What am I going to do? I'm going to pop and then push onto child stack. So we'll pop the G off, which physically removes it, and then push it onto the child stack. Then we'll spin back up. Does temp stack still have stuff? If I peek again, I find a B, not a null. What do? Pop push. So we pop the B, push it onto child stack. Spin back up. Does temp stack have stuff on it still? We peek, we see that, oh, we get a null. There's nothing there. Temp stack is empty. All right, so we're done with this while loop. So we fall out of that. Now we spin back up to this while loop. While there's at least one element in child stack or temp stack, do the following. Is there one element in one of these two guys? I'll peek at the top of child stack and say, oh, there's something there. I don't even need to check temp stack because I only required one element in one of the stacks. So I'll go ahead and say, okay, well, we're good. So then what do? I drop inside of this while loop and I say, okay, well, child stack has stuff. What do? We push the left and right children of peak child stack onto temp stack. So we peek at the top of child stack, we get B. And now we need to go and push his left and right child onto temp stack. B's left and right child are A and D. There's A, push. There's D, push. Okay, so we're push the left and right children of peak child stack onto temp stack. So I push them. That puts D first and then A. Kind of an important aspect of this. All right, so I did that. And then I say pop from child stack and push onto content stack. So I've I'm done dealing with B, so I can pop it from here and push it onto there. Does child stack still have stuff in it? It does. I peek at the top of it. I find something that's not null. I know there's stuff. What do? I push the left and right child of that guy, of G, onto temp stack. G has no left child, but he does have a right child. There's the I. So I'll push the I onto temp stack. And then I'll pop from child stack and push onto content stack. Pop, push. All right, so I'm done with this while loop. Well, I'll spin back up. We'll ask the question again. Is child stack have stuff? Is there anything in here? Nope. So that's what this while loop is now done for this time through. Now I move on to move the contents of temp stack onto child stack in reverse. So while temp stack has stuff, temp stack, does it have stuff? Yep. When I peek, I find the I, so what do? I pop push. So I'm going to pop the I off of temp stack, and I'll push the I onto child stack. Oh. Does this stack still have stuff in it? Yep. I peek, I find the D, I'll pop, I'll push. Does this guy still have stuff? Yep. I'll peek, I'll find the A, I'll pop, then push. Does this guy still have stuff? Nope. So I'm done with this while loop. I spin back up when I say, is there at least one element in either child stack or temp stack? I peek at the top of child stack. I find, yes, there is at least one element in there. So now what do? I get inside of this while loop. Now I process child stack. So I'm going to add the left and right child of A. Nothing. Onto temp stack. So kind of wasted my time, but whatever. Then I'll pop A, push it onto content stack. Spin back up. Is there still stuff on child stack? Yep. So I'll peek at the top of child stack. I see D. Let's go ahead and add his left and right child to temp stack. Here's D, left child, right child. So push C, then push E. C, E. Then I can pop from child stack and push onto content stack. Spin back up. Does child stack still have stuff in it? Yep. So I'll add his left and right child. I. He is a left child H and no right child. So we'll push the H on there. And we'll pop. Then we'll push. Then we'll spin back up. Does child stack still have stuff? Nope. So we fall out of this while loop. And now our goal is to move the contents of temp stack onto child stack in reverse. So while temp stack has stuff, which it does, I peek, I find the H. So we'll pop and push. Does it still have stuff? Yes. I'll pop and push. Does it still have stuff? Yes. So I'll pop. What was it? C. And push. Does temp stack still have stuff? Nope. Spin back up. Is there at least one element in child stack or temp stack? Yep. So what am I going to do? I'm going to go and I'm going to add the children of C, the children of EV, and the children of H. So we'll try C first. There's nothing. So try to add left, try to add right. There's nothing there. Pop. Push. Try to add left and right child of E. No left and right child. Then pop. Push. Try to add the left and right child of H. Nothing there. Pop. Push. Is there anything left in child stack? Nope. So child stack no longer has stuff, so we fall past that while loop. Then our goal is to move the contents of temp stack onto child stack in reverse. Does temp stack have anything in it? Nope. So we fail that while loop. That's a pre-check loop, so we don't even execute the body once. Spin back up. Is there at least one element in child stack or temp stack? Nope. So we're done with that outer loop now. And now we now know that child and temp stacks are empty, and all of our nodes are in content stack in reverse order. So we need to reverse them again to get our actual level first, our level first search, right? So now what we can do is we can maybe create an answer stack if we want. Start that guy off as empty. This is answer stack. Stick it here. Oh, that's weird how that works. So what will we do? We're going to say while content stack has stuff. What will we do? Pop push onto answer stack. So we'll pop H, push H, pop E, push E, pop C, push C, pop I, push I, pop D, push D, pop A, push A, pop G, push G, pop F. Well, actually, I'm pop B, right? Pop B, push B, pop F, push F. No, nothing in content stack any longer. So once this guy fails, then our final answer is in answer stack. We can visit the nodes in pop order. While answer stack has stuff, while answer stacks has stuff, what do? We pop and visit. So we'll pop the F, we'll visit. Pop the B, we'll visit. Pop the G, we'll visit. So on and so forth. Okay, which for us might mean just displaying it, right? So pop and let's just say display value. And that's the way we would visit it in order. That makes sense? So, easy. Now, so look at this so far. We've just spent, what, 40 minutes or so? 30 minutes. We babbled for a little bit at the beginning. So let's say a half hour. Designing our algorithm. We have not written one line of code. This was the important part. So now that we have this written, okay, we got the logic down, translating this into code shouldn't be a big deal, right? I mean, we need to have a couple of stacks, and our stacks need to be capable of holding the kinds of values that we're holding. So let's look at what kinds of values we're holding as a reminder. All right, so we have this thing called binary tree. So we converted our stuff last time. We have a binary tree of binary trees, right? Okay, so we have a left and we have a right tree. So we're going to be, and every binary tree also has a payload. All right, so we need to now have a stack capable of holding binary trees. Something we need to be able to have. Let's see, have I shown you the generics yet from Java? The angle bracket things? You're just agreeing with her? Okay. Have I shown it in here? Are you sure? Are you lying? You lied to her. It's a bubble water thing.
Like has the E for like the generic.
Yeah.
You put like linked list or binary tree in it, right?
Right. So let's look at the Java documentation here, just to see what we have available to us. I want to say there is not a stack data type in Java. I think we could just use linked list to pull this off, but I mean, a stack is just a baby linked list, right? That we use in a certain way. Let's see if that's the case. Very nice. Oh, there we go. Java APIs. C8. I'll just go with the in order things down to S. Just not sure if they actually wrote a stack or just assumed you would always use linked list to implement stacks. Because I would prefer to have something that has pushes and pops in it. Stack. Yeah, we have it. So there's stack, there's peek, pop, push. We also technically have a search, but that's not a typical stack thingy. All right, so this looks like our normal stack. Oh, we also can ask if it's empty. We don't even have to do the peek thing. All right, so even better. Okay, so we're going to go ahead and create a Java stack for these three things. So we'll get the ball rolling with this. So when we have our binary search tree, we had our visit pre-order, visit post-order, visit in order. So now let's write visit level order. Public void visit level order. Like this. And just as a reminder, in our main activity, yeah, here, we filled it up with the same values that we had before, right? So we added those to our tree, so it should match our output that would allowed us to check. Okay. So we hard-coded our tree, so to speak. So visit level order, this is going to require us to do what we talked about here. So we need 4 stacks at the end of the day, right? 4 stacks for holding binary trees. All right. So we're going to create stack answer stack is equal to a new stack capable of holding our binary trees. All right, this is what? Option enter. There we go. So that's our answer stack, and this is going to be a stack of binary tree. I think the other syntax would have worked, but this is the cleaner way of doing it. So I want to create a stack of binary trees. That's the type of variable I'm building. It's going to be called answer stack, and it's going to be equal to a new stack of binary trees. This is that thing called generics. Because if we don't use this, that stack will hold blank objects, generic objects, which is fine. But what we'll have to do is when we pull the value out, we will have to recognize that what we actually put in was a binary tree. So we'll have to cast it back to a binary tree so we can do binary tree stuff with it. Because as far as Java is concerned, it's a generic object that it's pulling out of there. Okay, even though we happen to know that it's a little bit more than that. Using generics here effectively has Java doing the typecasting for us. We'll put in a binary tree, it will come out as a binary tree because we've told it, I intend to store binary trees in this stack. Make sense? All right. So now we have our stack binary tree. Content stack is equal to a new stack binary tree. Stack binary tree. It's called what? Child stack. a new stack binary tree. That. All right. And then finally temp stack, stack binary tree temp stack is equal to a new stack binary tree. All right, so that is our that's our current stacks that we're going to need for pulling off this algorithm. All right, so we start off, we're at the top here. If root is not equal to null, push onto child stack. So we have something up here called root, which is a binary tree. So we ask the question, let's see, where am I at here? If root is not equal to null, then we're going to say child stack dot push this dot root. Here, I'll say this dot root here just because that's how I like writing it. All right, so that part is done. And we're only going to do anything here if root is not equal to null. If root is equal to null, what do we do down here? We just printed empty tree. Yeah, so actually, if we want to follow our exact cadence from down here, let's just do this. There's our else. Our else will be child stack dot push this dot root. Okay, so we pushed root onto the child stack. Now we need to write the code for this while loop. So while there is at least one element in child stack or temp stack, do the following. So we have to write a while loop that says if there's at least one element in either child or temp, keep going. So while child stack is not empty, or temp stack is not empty, while at least one of those guys is not empty, we're going to do some stuff. Make sense? All right, this is just paint by number at this point. We're following our algorithm. So while at least one of those guys has stuff, do that. This loop says while child stack has stuff. So here's our two loops, and let's put some comments in here. So we're going to say clear child stack by adding its children to temp stack and then popping. All right, so while not child stack dot is empty, while there is stuff in child stack, do our logic here. All right, we can even put that stuff in there. So what does it say to do? So let's do that. Then it says do this. All right. Then, while temp stack has stuff, while not temp stack dot is empty, what do we do? Okay, and what are we actually accomplishing with this guy? Accomplishing that. Push pop. So there's our while loop. There's our 2 while loops inside of it. So we just need to write the code for these things. Write the code for this thing. After this while loop is done, we now know that child and temp stacks are empty and all of our nodes are in content stack in reverse order. So we need to reverse them again. And here, let's, there we go. So it's a little more readable. So what do? We have our while loop while content stack has stuff. Pop push. Pop push onto answer stack. Now we know that our final answer is in answer stack. We can visit the nodes in pop order. So while answer stack has stuff, while not answer stack dot is empty, pop, and display value. So that will be our algorithm for visit level order. Okay, so your homework assignment is to finish this algorithm by converting our little comments here into actual code. Should be pretty easy now that we went through this entire thing. Now hopefully what you saw from this is how quickly the code went once we spent the time designing the solution. Make sense? Now let's just quickly ensure that this guy, so here we're visiting in pre-order, post-order, in order. So in the end here, you should have a tree.visit level order. So we'll go ahead and put that in there. That should display it in level order. Make some sense? All right, so I'll go ahead and push this. Should be an easy assignment for everybody, as long as you take your time and follow those comments. And hopefully you learn from this lecture that your time will be well spent doing something like this for future homework assignments. All right, so let's commit changes. For level one second. Commit and push. Commit, push. Just stop the recording and get it uploaded before I forget.